Now that you've seen rate laws for chemical reactions, let's talk a little bit more about temperature and how that can affect the rate of a reaction. Remember, we said there were different factors that affect the rate of a reaction. Okay, so earlier we talked about things like concentrations and pressures. Now we're going to focus on temperature and see what that does. Okay, and so the first person to really figure out how temperature affects the rate of a reaction was Arrhenius. This is the same Arrhenius as the person who figured out the Arrhenius theory for acids and bases. Okay, and so there's something called the Arrhenius equation that allows us to determine how the rate is going to actually be affected by temperature. So let me show you what the Arrhenius equation looks like. Okay, the Arrhenius equation basically looks like this. It says that K is equal to A times E to the minus activation energy over RT. So let me give you a few words and descriptions about this thing. Okay. Remember earlier when we talked about rate laws and I said there's a thing called K, the rate constant? Well, now I'm going to tell you that this rate constant isn't really truly exactly a constant. Okay? It's actually a function, and it's a function of temperature. So this is a thing that actually changes when temperature changes, right? Concentrations don't really change when temperatures change. So if I look at the rate law, it was K times concentration to some power. If the rate's going to change and the concentrations aren't changing when temperature changes, it has to be the K that changes when temperature changes. Okay, and so this rate constant is really a function of T. And this is the equation for that. If I just take the natural log of this, okay, natural log of K is equal to natural log of A minus activation energy over RT. Or if I rearrange this a little bit, natural log of K equals natural log of A minus activation energy over R times 1 over T. And you say, why the heck would I want to do that? Well, I want to make this look like a straight line. Okay, and so a straight line has the equation y equals mx plus b. Okay, so now if my y-axis is my natural log of K, and my x-axis is 1 over time, 1 over temperature, okay, then I can see by this equation that my slope is really minus the activation energy over R. And my intercept over here, the y-intercept, is the natural log of A. Okay, and so let me give you a little more details about this Arrhenius equation. Okay, so in the Arrhenius equation, I have these different variables in there. Okay, there's an A and there's an activation energy. Okay, and so the pre-exponential factor A represents what the fastest possible rate is for the reaction, which basically means if nothing else was an issue and I was allowed to do things like diffusion, okay, how quickly could this reaction possibly take place under the best possible circumstances? So I can think of this as being related to the rate of the reaction in terms of successful collisions between the reactant molecules when they come together to make product molecules. Okay. The other thing in the Arrhenius equation is this EA, activation energy. Okay. Activation energy is the minimum energy required that these molecules have to have for the reaction to happen. Okay. Only the fraction of molecules that have an energy greater than the activation energy are going to be able to overcome it and carry this reaction out. So according to the Arrhenius equation, if you look at it, it actually looks like an exponential decay, okay? Sometimes called a Boltzmann distribution. So only the molecules that have enough energy to equal to or greater than the activation energy are going to be able to form products, okay? Which basically means that the higher the activation energy, the more the rate constant will depend on temperature. The higher the activation energy, the harder it's going to be for that reaction to happen because I'm going to have fewer and fewer molecules with enough energy to be able to cross over and form products from that. Okay, and so relatively fast reactions have very small activation energies, and very slow reactions tend to have very high activation energies.